Welcome to Daemon Automation's Factory Floor AI podcast series.
We are looking at the world of high-speed industrial automation. And the real challenge here, it's not just about being fast. It's about getting that frame-perfect timing for AI inspection. Not just once, but every single time one of those critical intermittent events happens on the line.
Timing is absolutely the silent killer of efficiency on the factory floor. We're talking about microseconds. If you miss that critical moment, the part is moving, you get motion blur, mispositioning, and
That is useless.
it's worse than useless. You've wasted processing power to get a bad result.
And that really brings us right to the core of what we're dissecting today. Daemon AI's trigger camera mode, or we'll call it mode 2. The whole system is engineered so that your AI inspections are as precise and reliable as if you had a master inspector on the line.
One with, absolutely flawless, repeatable timing every single time.
Right.
But it's important to ground this conversation. I mean, the established foundation for Daemon AI is run mode, or mode 1. And that's the incredibly robust method for general continuous inference. It's always watching. It's the reliable bedrock of the system.
So if mode 1 is already so robust, so reliable, why create this specialization? Why build a whole new mechanism in mode 2?
Because continuous processing, as powerful as it is just incredibly resource intensive when you're dealing with events that happen, intermittently.
Just for a brief moment.
Exactly. Think about a high-speed production line. It's running at, say, 30 frames per second, but your quality check only needs one single crucial inspection every 3 seconds, right when the part is perfectly still.
So in those 3 seconds, that's 90 frames?
90 frames. In continuous mode 1, you're asking this incredibly powerful AI to process all 90 of those frames.
Even though only one of them actually matters.
Only one has the useful inspection result. You're just consuming resources, generating heat, taking up processing cycles for 89 useless frames. Mode 2 is the optimization. It's designed to eliminate that massive inherent resource cost. We've basically engineered the waste right out of the system.
That sounds like a genuine paradigm shift. You're going from processing everything just in case to processing only the perfect moment.
It's a shift from digital brute force to high-level specialization. Let's use an analogy for this. Continuous processing, mode 1, is kind of like a frantic tourist.
Yeah.
They put their camera on rapid-fire mode, they're snapping 100 pictures, hoping one of them happens to be in focus and captures the right moment.
Right. Spray and pray.
Exactly. But the new trigger camera mode, mode 2, that's the professional photographer. They aren't constantly draining the battery, filling up the memory card. They wait patiently for that single decisive moment.
And that's the key. It's not about a flaw in the old system. It's about specialization for a specific problem.
Precisely. We're solving a timing problem with perfect timing, not just by throwing more speed at it.
So the mechanism behind this efficiency, you call it the power of one. How does that actually work in the system?
Well, the AI system literally pauses. It consumes almost no processing resources while it's in this waiting state. It's effectively dormant.
Okay.
When that external trigger, that signal that the decisive moment has arrived, when that comes in, the system instantly wakes up. It performs exactly one perfect, frame-accurate inspection.
Just one.
Just one. And then it immediately returns to that paused, waiting state.
So instead of pushing 90 frames through the pipeline for one good result, you activate the whole AI engine once. That must be revolutionary for throughput and just system stability.
It is. And crucially, that frame-accurate control completely eliminates the motion blur and mispositioning issues that have, always plagued high-speed continuous inspection.
That's huge. But let's get specific, because these benefits aren't just theoretical. I mean, you have to tell us, what kind of resource savings are we talking about here?
We have optimized the precision and the operational states of the system to reduce resource demand by a phenomenal 90%. And this metric is the direct result of smart engineering. It allows this highly capable AI to essentially idle, consuming almost no processing power while it waits for that one perfect signal.
Wow, a 90% reduction in processing power while waiting? That's massive. But how does that change the type of hardware factories can use, or even just the operating conditions on the floor?
That 90% reduction translates directly into really tangible operational benefits. I mean, think about heat. When the processing system only spikes for one frame and then immediately idles, you generate dramatically less heat overall.
Which is critical. I mean, these systems are often running these tiny sealed industrial enclosures.
Exactly. And passive cooling can fail pretty quickly in those situations. Less heat means reduced cooling costs. You don't need these elaborate active cooling systems. But maybe even more importantly, that reduction in heat and stress, it results in a much longer lifespan for the inspection hardware itself.
Lower stress, more reliable system, better ROI.
That's it. It stays operational longer, which enhances the ROI of the whole setup.
Okay, so we've solved the resource problem. Let's talk performance. How reliable is the timing itself? If the system is paused, how do you deal with the risk that a fast-moving part is already gone by the time the AI gets the message to inspect?
That's a crucial question. We achieve incredibly tight timing control. Our trigger response time, so the time from the system detecting the command to the inspection actually happening, is only 0.1 seconds.
100 milliseconds.
100 milliseconds.
For someone who isn't technical, why is that specific number such a game changer compared to older vision systems?
Because it moves you from hoping to catch a good frame to absolute certainty.
Right.
In high-speed scenarios, delays compound so fast. In older systems, API calls or complex data parsing could introduce variability of hundreds of milliseconds, maybe even seconds. A conveyor could move apart dozens of inches in that time. By guaranteeing 100 milliseconds, we eliminate that uncertainty.
Which means what, in the end?
Frame-perfect timing, every time. And that leads directly to zero missed inspections due to timing issues. We are removing one of the biggest variables that causes problems in these really high-speed environments.
So for this to work, you need a really reliable industrial handshake. You need the physical sensor on the factory floor to talk to the AI system. And that bridge is the PLC, the programmable logic controller.
The PLC is the true brain of the factory floor, and our bidirectional communication system lets the AI listen directly to it. The sensors, they first report their status to the PLC, signaling a part is in position or a belt has moved exactly 10 feet.
And what's the critical piece of information the PLC sends to the AI?
When the PLC confirms the timing is perfect, it converts that decision into a standardized command value. It's just a single integer. In this case, it's 2 for mode 2 single trigger.
And that's a deliberate design choice, just sending a tiny piece of data.
Absolutely. It writes that single integer into a specific, highly prioritized communication slot we call the standardized command register. It's within the industrial interface connecting the two systems.
And that must be why the system can hit that incredible 0.1 second speed.
Exactly.
It's not processing some huge data set or parsing complex network traffic. It's just waiting for the PLC to write one tiny integer into this one specific place.
Precisely. We are constantly monitoring that dedicated slot. We minimize all the processing overhead and avoid the latency you'd get with, traditional API calls or database lookups. We're only reading a command to change our state. That makes it instant.
That makes perfect sense. So let's look at the factory side. What kind of physical inputs can the PLC use to generate that load 2 command? I imagine the versatility is pretty important.
We see 4 primary types. Starting with position-based triggers, we have encoders.
Encoders are fantastic for that sub-millimeter positioning accuracy.
Exactly. They measure exactly how far something has moved. So the PLC can be programmed to trigger the inspection only after the part has moved exactly, say, 12.00 inches, perfect for bottle filling or component placement.
And next, for just simple presence detection.
For that, you have photo eyes. They're just simple light beam breaks. A part moves into the area, breaks the beam, the PLC gets the signal instantly and sends the mode 2 command. It's fast, inexpensive, and great for continuous motion.
Then you have the more definitive physical confirmation. Limit switches.
Right, limit switches are mechanical. The part has to physically press the switch to signal it's fully seated or secured in a jig. That's crucial for things like heavy stamping operations, where mechanical stability is an absolute must before the AI takes its shot.
And finally, you can bring the person back into the loop with operator buttons.
Right. If you have a complex assembly that needs a human to align it or confirm a step, the operator just pushes the Inspect Now button. That manual action instantly tells the PLC to send the command. It's where human experience meets AI precision.
And the flexibility is huge, too. We should mention the PLC isn't just limited to mode 2. The system supports independent camera control, right?
Absolutely. You could have one camera stay in mode 1 for, general monitoring of the environment, while 8 other cameras are all waiting on specific independent mode 2 trigger commands.
And the PLC can set other modes using that same command register.
Yep. It can dynamically set mode 0, which is ignore tells the system to skip all processing to save even more energy. Or mode 3, which is save MP4. That triggers an immediate video recording from the buffer, which is great for process review later.
That level of dynamic control, all run by the factory's existing brain. That's what makes the system so adaptable.
It's the ultimate expression of control and efficiency.
This whole discussion, going from continuous processing to this trigger camera mode,
Hmm.
it really solidifies this concept of surgical, precise energy use.
It's a fundamental shift in philosophy. We're moving away from brute force. We use power exactly when and where it's needed for exactly one perfect result.
Okay, so let's use one last analogy to really drive that home. The shift from continuous processing to trigger camera mode is.
Right.
It's like swapping a garden hose that's just running constantly, wasting water all over the floor,
Right.
for a high-powered water jet nozzle that's activated only by a foot pedal.
You got it. You only use the immense power of the system when you need that single, perfectly timed, focused burst of energy. You get massive savings and precise application every single time without the waste.
Which brings us to our final thought for you to chew on.
Oh.
We've established this bidirectional communication. The AI can listen to the PLC to manage all four modes: ignore, run, single trigger, and save MP4.
And this is where true system-level intelligence really starts to come into play.
So the critical question is this: how could an industrial engineer leverage that inherent capability to dynamically switch between all four of those modes based entirely on external real-time process factors, not just for inspection, but for the entire factory system?
Think about using process intelligence to drive efficiency. For example, if an upstream machine signals a major fault or goes down for maintenance,
The PLC could just automatically write mode 0, ignore, to all the AI cameras in that zone.
and instantly conserve all that energy. Automatically.
And conversely, what if a high-value batch starts, one that needs strict positional accuracy?
The PLC could dynamically switch from mode 1, run, to mode 2, single trigger, just for that specific batch. It guarantees perfection, and then switches right back to continuous monitoring afterward.
That level of autonomous, dynamic system management, using the real-time status of the factory to control the AI's processing schedule. That's what extracts the absolute most value out of this kind of capability.
That's the ultimate goal of efficiency. This is what intelligent automation looks like. To learn more, visit daemonautomation.com.